Yes, this is 300 Plus Academy, where all we do is exams tutoring. Our aim is to ensure that you ace your next exams and you perform excellently well. Do like, comment, subscribe, and turn on the notification bell for our YouTube channel at 300 Plus Academy. So today what we have for you is the General Certificate Examination, shortened as GCE, Physics Alternative to Practical. When we say alternative to practical, it simply means you're not going to be performing that experiment. The experiment had already been performed. So what you are going to be doing is to read the data, to read diagrams and interpret, plot graphs, and of course answer questions that ensue in the course of those interpretation of data. The experiment we have today for you, which is a probable question in this GCE, is about a loaded test tube. A loaded test tube, let's say this is a test tube with, let's say, something like stones. We call this lead shot, immersed in water. Let this be water. So what this means is that the test tube has the tendency to oscillate, to bob up and down, more of a periodic motion, so that in the process we begin to talk about period. That's the time it takes to complete one oscillation or one cycle or one to and fro movement. But let's get into what the question is saying, what the examiner wants here. It says a test tube is weighed and its mass MO. So which means we have the mass of an empty test tube, which is 20 gram. Now, this test tube is loaded with lead shot. So test tube plus the lead shot is the lead shot we put in the test tube. Of course, we tag that MX. We call that MX. So the mass of the lead we are putting into the test tube is tagged ME. So it now means if I want to know the mass of the lead, it is going to be the mass of the entire test tube, inclusive of the lead shots, take away the mass of the lead shot, which is 20 gram, which we were given in the question. Okay, straight into it. The first instruction we were given is we were told to record the masses ms of the loaded test tube, as you can see in figure 1a. For the first recording, that's why I have serial number 1 to 5 here, because the experiment here was performed repeatedly 5 times, so that we get accurate result. Okay, so the first reading for mx of course is in gram, is the talks about the mass of the test tube and the lead shot in the test tube. When read on figure 1a, we have 50 grams, we have 53 grams, we have 55 grams, and we have 57 grams, and lastly 60 gram, of course avoiding parallax error. So you need to understand something. As the masses here is increasing, the mass of the test tube is constant, which stands at 20 grams. As we increase the amount of lead shot that is inside the test tube, so does mass ms increases. And so also you must have noticed a pattern here. The more the lead shot you put, the more the test tube is a mass, the more the depth to which the test tube sinks in the fluid or the liquid. So when the mass of the whole setup was 50 gram, as you can see on display, figure 1b, measuring from the 0 centimeter mark, the depth D1 is 7.70, the depth D2 is at 8. When the mass is 55, the depth is at 8.4. When the mass is at 57, it's at 8.70. And when the mass of the whole setup is at 60 gram, the depth had even gone further to 9.10. So which tells us that the more the lead shot, the more the depth of immersion. So we've been able to record that. Also take note of your unit. This is in centimeter, this is in gram, and that covers for the whole reading from 1 to 5. Also, that's for Roman figure 1. We were told to read and record the masses mx of the test tube and the lead of the loaded test tube. That's the test tube and the lead shot. Then the depth of immersion, Roman figure 2, we were told to measure and record that. We've done that. Then we were told to read and record the corresponding time t on the stopwatch for 10 complete oscillation, which means that the test tube was allowed to oscillate up and down, up and down, up and down 10 times. That is 10 complete oscillation. And the timing it took, we were told to record that for 10 complete oscillation, as you can see on figure 1c. Of course, the first one we have 6.5 when for the first reading. Figure 1c on your screen is talking about the timing it takes to complete 10 oscillation. It was 6.50 for the first reading, 6.80 for the second reading, 7 for the third reading, 7.40 for the fourth reading, and lastly for the fifth reading, 7.50. Okay, that ends that for Roman figure 3. For Roman figure 4, we were told to evaluate in each case ME. That's the mass of the lead shot. Mass of the lead shot. Now, mass of the lead shot is actually the mass of the setup, the lead and the test tube taken together. Take away the mass of the test tube. That's what you see here. MX. That's what you see here. Mass of the lead shot is MX. Take away 20 gram, which is the 20 gram for the test tube, so that we can get the real value of the lead shot that has been loaded into the test tube. So MS, take away 20, 50 take away 20, 30, 53 take away 20, 33, 55 take away 20, 35, 57 take away 20, 35, and 60 take away 20, 40 grams. So we've been able to do that. On Roman figure 3 displaying, Roman figure 4 displaying, we were told also to express for the period of oscillation. Like I said, period is the total time taken divided by the number of oscillation, which means that if this test tube has been allowed to oscillate 10 times, 1, to and fro 1, to and fro 2, to and fro 3, to and fro 4, 10 times, and it's taking 6.50, then the time it will take for just one oscillation should be 6.50 divided by 10. The total time it takes divided by 10. Take a look at it again. Think about it. Something was allowed to oscillate 10 times. And let's say it takes for the first reading, it takes 6.50 when the oscillation was allowed 10 times. Then it means for one oscillation, that must be 6.50 divided by 10. And that's why we say period is the time taken for one complete oscillation. So that's the time taken divided by the number of oscillation. In this case, that is 6.50 divided by 10, and that's why we have 0.65. That's why I put it here. The period is in seconds, and that will be the total time divided by number of oscillation, which is 10. So 6.50 divided by 10, 0.65. 6.8 divided by 10, 0.68. 7 divided by 10, 0.7. 7.40 divided by 10, 0.74. 7.5 divided by 10, 0.75, all to 2 decimal places. And of course, the period is in seconds. The seconds covered for all of the reading. That is on Roman figure 4. On for question Roman figure 5, question V, it says also evaluate t square. That is the square of the period. The square of the period. So which means 0.65 square is giving me 0.423. 0.68 square is giving me 0.462. 0.70 is giving me 0.49. 0.74 is giving me 0.4548. 0.75 is giving me 0.563. It's giving me 0.563. And that's what we have here for t square. So the unit is going to be in seconds square. Lastly, on the fifth reading, we we were told to evaluate the quantity L. The quantity L. L is given as ME over D. That's mass of the lead shot divided by the depth of immersion. So which means that's why I am not putting this here. I am putting it closer to D and to the mass of the lead shot so that you can really be able to compute that. 30 divided by 7.7, you're going to get 3.90. 33 divided by 8, you're going to get 4.13. 35 divided by 8.4, you're going to get 4.17. 37 divided by 8.70, you get 4.25. 40 divided by 9.10, you're going to get 4.40. Take note of the unit. I was told to evaluate L, but I wasn't told the unit. So it is left for me to write out the correct unit for that. So if my mass is in gram and my depth is in centimeter, that means that my L will mean gram per centimeter, and this unit covers for everything you have for L. And we were told to tabulate our reading on Roman figure 6, which is exactly what we have done here. Okay, on question Roman figure 7, VII, we were told to determine the mean value of Q. Mean value of Q. Mean value of Q here means average, the arithmetic mean of my L. So the arithmetic mean of my L is 3.90 plus 4.13 plus 4.17 plus 4.25 plus 4.40, all divided by 5. And I'm getting 4.17 gram per centimeter. The next thing on Roman figure VII, that's Roman figure 8, is about we plotting a graph of ME, that's the mass of the lead shot, as against the T square, that's the period square. That is what we are meant to do now. Okay, to get that done, the very first thing we are going to write for Roman figure 8 is to talk about the graph. The title of our graph is the first thing. We say graph of ME, that's the mass of the lead shot in grams, against T square in second square. So which means M is going to make my vertical axis, and then T square in second square is going to make my horizontal axis. So what are you going to need to be able to plot your graph? You need on paper, if you're plotting on paper, you need your 30 cm, yes, 30 cm meter rule. You need a very sharp, well sharpened pencil. You need your eraser. I think just about those three are the important tools you need to be able to plot that. But of course, I have my own ruler here. It's a meter rule I have here. It's 100 centimeter. That's a meter. So I'll be using this to plot my graph. I'm going to avoid broken lines. I'm going to avoid too thick lines. I'll just try to, do things that will impress the examiner, and of course so that I can get my full mark. Remember that your physics alternative to practical, it's a 50-mark exam, and for someone who wants to get a grade A or at least a B in physics alternative to practical, the starting point is to make sure that out of the 50 mark for your alternative to practical, you don't get anything less than 45 out of possible 50 marks. So let's get right into it. We want to plot a graph of ME against T square. Of course, the very first thing you want to do is you want to draw a line for your vertical axis, and I'm going to do that right away. It's going to be just a line, no broken lines. You can see that, just one line. And regardless of the figures I'll be putting on my horizontal axis, regardless of the figure, I just want to get out here the right I want to get on here the right drawing for the horizontal axis. Okay, I've been able to do that successfully, so that okay, that I've done. Of course, it's a lot more easier when you are plotting your graph with a pencil as against using a whiteboard marker, of course. But regardless, the important thing is for you to get the scope. So I'll be starting both from the zero origin. So let me quickly look at the figures I'll be writing out for. Of course, this is ME. Let me put it there again. ME in grams. And then my T square in second square. So what I want to do now is that I want to write out, okay, let's see. My ME, the smallest figure for my ME is 30 and the largest is 40. Should I tend to that? Of course, it's a lot easier when you're plotting with your pencil as against when you're plotting with a marker. But regardless, so I'll be starting both graph from the zero origin. So let's look at the values for my ME, the mass of the lead shot. I have 30 gram, and that's the smallest, and the largest is of course 40 grams. So I'm thinking 10, 20, 30, 40. Okay, so that in case you don't know, from here to here on your paper graph, that is 2 centimeters. So I'm going to take here to here as 2 centimeters. So I'm thinking of 2 centimeter, 2 centimeter, that is 4 centimeter. Come in, let me get that part right. Okay, 4 centimeter, 4 centimeter, 2 centimeter, 2 centimeter, 4 centimeter to represent 10 units. 10.00 units. And of course, another 4 centimeter, that's going to be 20.00 units. And then 30.00 units. And then 40.00 units. That's that for my ME axis. That's the vertical axis. And then for the horizontal axis, I am dealing with T square. The smallest is 0.423 and the largest is 0.563. So what I'm going to do to that is, okay, I'll take from here to here 2 centimeter, from here to here 2 centimeter. You can see here to here is 2 centimeter, here to here is 2 centimeter. So that's the same thing on paper. So I'm thinking 0.1, 0.2. I'm thinking 0.4, 0.5, that's 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. And that covers a large portion of the graph. So I'm going to start with that, and that is 0.100, 0.200, 0.300, 0.400, 0.500, and 0.600. Okay, so with this, I am now going to try to plot in the exact positions for each of the readings. Okay, so I have 30. When ME, mass of the lead shot, is 30 gram, my T square is 0.423. So 30 gram, this is 30 gram here. And then I have 0.423. So let's try to locate that. 0.41, 0.42, 0.43. 0.41, 0.42, 0.43. If I trace that up, okay, if I trace that up to 30, so this is the point here. Okay, I've been able to get that out. And then the next one is 33. When my ME is 33, I'm talking about 0.462, 0.462, 0.41, 42, 43, 44, 45, 462 should be somewhere in between here. I'll try to locate that. And 33. 33 is going to mean, okay, somewhere here, I'm coming, somewhere here. This is 30. You need to know 1, 2, 31, 1, 2, 32, 1, 2, 33, 1, 2, 34, 1, 2, 35. So I need 33. So 1, 2, 31, 1, 2, 32, 1, 2, 33. So that's I'll try to locate. 33 is what I need, and so that is going to be at this point. Okay, so it is at this point I've been able to get that out. Okay, let me make that clearer. Yes, I've been able to get that out, and then I can take this off so that I have a very neat graph. And then the next one is 35 and 0.49. This is 35 and 0.49. This is 0.49, but we have yes, exactly 0.49. So it's at this point. It's at this point. So I've been able to do justice to that. Okay, so to the next one, I am talking about 37 and 0.548. This is 35, 36, 37 is here. 37, and I'm looking at 0.548. This is 0.51, 52, 53, 54, 55. So it's somewhere in between here. I'm going to trace that up. I'm going to trace that up. I'm going to trace that up. Okay. I'm almost there. Okay. Somewhere here. So that's what I have. Okay. I've been able to do that. So we then talk about the last reading. Let's try to pinpoint that. 40 and 0.563. 40, this is 40 and 0.563. So let's try to look at that. 0.51, 52, 53, 54, 55, 563 should be somewhere here. 563 should be somewhere here. So if I trace that up, so that should be here. Yes, that should be here. So I'll mark that, and with a dot, of course, with a dot. So that I've been able to do. I've been able to pick my 5 points. I've been able to pick my 5 points. Now the next thing for me to do is to try. Okay, I've been able to plot the graph of ME on the vertical. I've done that. Now to question 9, IX. Now I was told to determine the slope X of the graph and the intercept C on the vertical axis. Next question is question IX, that's Roman figure 9. We were told to determine the slope from this graph we had actually plot. We want to determine the slope. Okay, we want to determine the slope from this set of points. To determine the slope, we know that normally in mathematics, when we want to get the slope, it is always y2 minus y1 divided by x2 minus x1. This is the normal standard for getting our slope. But in this regard, let me try to pinpoint that and use the right wordings. I also recall that for question IS, to get the slope and the intercept on the vertical axis. So how am I to do that? Let me show you very quickly. So I will try as much as I can to pick up points. Yes, I will try to pick up as many points as I can. Out of the 5 points, it will be good if I can pick out at least 4 points, and of course get a figure on my and also get a figure on the for the intercept on the vertical axis. I've been able to pick point, 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 and of course maybe I can do some adjustments to the last one. So as I plot that, and let's see the figure I'm going to get for that. Okay, here we go. So let's see what that looks like. Okay, I was able to pick out 3 points. I was able to pick out 3 points. Like I said, it's a lot more easier to draw your graph with a pencil other than with a whiteboard marker. But regardless, this is a good one. Now, where the straight line touches on the vertical axis, that is your intercept. This is my intercept here. Where the straight line touches on the vertical line is my intercept. Intercept is C. Intercept C. Okay, let me make that a bit clearer. Intercept C. Okay. And when I look at this, this is 0.5, 1.5. This is at 1.5 on my graph. That is my intercept. Okay, I've been able to do that. And also I was to get the slope. Okay, the slope or the gradient, that's going to be changing the vertical, changing y. So this is how I'm going to go about my slope. Okay, I can pick up any point. I'm going to pick up any point. Okay, I'll try to make it as big as possible. Okay, this is going to be my change in ME in grams. Change in ME in grams. And then this is going to be my change, delta t square in seconds square. So now that I have this, I am going to, via extrapolated line, try to get those figures on the horizontal and vertical axis. So that it's easier for me. Okay, this is on this point. Okay, these are 10. And of course, I'm picking this here. Oh, of course, you can make use of your ruler to get that. So this is 40.5. So talking about my slope here, my slope here should be change in ME in grams divided by change in t square in second square. And what this means is 40.5 because this is 40. From here to here is 0.5. 40.5 minus here is 10. X2. So y1 is 10. Divided by my t square. For my t square, what I have x2 there is 0.5, 0.51, 52, 53, 54, 55, 56, 57, 0.57, 0.57, take out 0.1, 0.11, 0.12, 0.11, 0.12, that's 0.125, 0.125. I'll take that again. 0.1, 0.11, 0.12. This should be 0.13, but of course, it's not getting there, so that's 0.125 in between. So when I subtract this, 40.5 take away 10 is going to give me 30.5. Recall this is in gram. Because of my unit, this is in second square. So 30.5 gram divided by 0.570, take away 0.125, that's 0.445 seconds square. Okay, so 30.5, that will give me 68.5 gram per second square. That is my slope. I've been able to answer question IX. Now the next question talks about, that's question 10. Question 10 says, evaluate K equals to 4 pi square x divided by Q. 4 pi square x divided by Q. And so that's going to mean 4 times 22 over 7 times 22 over 7 times, my slope is 68.5. And of course, I have a Q. There was a point where I was told to look for the mean value of L tagged as Q, evaluate Q. Value for my Q, which we expressed on question 7, VII. The mean value for my Q of LI is actually 4.17. But take note of the units. This is gram. This here is in gram per centimeter square. Sorry, gram per centimeter. Yes, just gram per centimeter. Whereas for the slope, that is in gram per seconds square. Take note of the unit. This 4 is a constant. This pi 22 over 7 is a constant, and the slope, okay, that has a unit. For your Q, which is the mean value for the what we calculated on Roman figure 7, Q of Li, that's in gram per centimeter. So what my unit should look like here, let me talk about my unit first. Gram per second square times, of course this will turn upside down, centimeter divided by gram. So gram should take out gram. I should have centimeter per second square. I know that that's going to be my unit. So 649.03 centimeter per second square. That is for X. Now I have for question Roman figure 11, XI, precautions. State 2 precautions that are necessary to ensure accurate results when performing this experiment. What are the precautions? Okay, XI. Let me put my precautions here. Precautions when performing this experiment. The first one is to avoid parallax error when taking my reading on the stopwatch. Also, when taking my reading on the meter rule to measure the depth of immersion, also on the meter rule. Also on the weighing balance. Weighing balance. Okay. When we talk about parallax error, let me just give you what that means briefly. Okay, this is my meter rule. If I want to measure something, I am to look at it. This is a meter rule. Let me talk briefly about parallax error. This is a meter rule. If I want to measure something, I am meant to look at it just vertically, not sideways, as that is going to affect my judgment. You understand? I won't be able to get the precise figure, but when I look at it vertically, that way I can actually get the right figure. So it means that for this experiment, one error I need to ensure that I avoid is parallax error when taking my reading on the stopwatch as on figure 1A, on the meter rule as well when measuring the depth of immersion of the test tube when loaded, and also on the stopwatch. The second error I need to ensure that I avoid is to ensure that the test tube is standing vertically. Is to ensure test tube is standing or floating vertically and not bending sideways. Another error I must avoid or try to correct that is this error we call zero error. I'm going to correct zero error in my stopwatch, and also I can correct that on my meter rule. When we talk about zero error, zero error is a situation where an instrument gives a reading when the true reading at that time is zero. Take for instance, I want to measure the time it takes for this oscillation, but the stopwatch itself is not on zero, but had actually moved forward a bit. So which now means by the time I start my counting, I will be giving more time than expected. So to correct that, I need to make sure that I correct zero error from every of the instruments I am going to be using. So I am told to list 2 precautions here, but I've been able to list 3. If you know of any other, of course you can continue to list, but the examiner wants to, and you are to give exactly 2 in your exam. Okay, let's move on. That is the end of question A. Now we talk about question B. It says, list the forces acting on the test tube as it performs vertical oscillation in water. What they want here is for you to, list the forces acting on a floating body, because what we have here is a test tube. What we have here is a test tube floating, a test tube loaded and floating in water. Okay, B1, I'm to talk about the forces. Okay, let this be the water that I have, and let this be my test tube, of course, loaded with lead shot. So I'm to talk about the forces acting. Yes, one of the forces acting here, which we are all conversant with, is first the weight of the test tube and the lead shot. As well, you can call it gravitational force, tagged mg. That's the one of the force. Another force acting here is what we call upthrust. And then another force acting here is what we call viscous force. Viscous force, or simply force due to liquid friction, trying to resist the movement of the test tube. You can see the viscous force and the upthrust, they are acting upward, whereas the weight is acting downward. Viscosity talks about the resistance of the flow of the liquid. It's trying to prevent the test tube from further sinking or being immersed into the liquid. So these are like the 3 forces acting here. We were told to list the forces, and that's about 2 marks. We've been able to do that. And then B2, which is the last question for this, explain why the amplitude of the oscillation of the test tube decreases with time. Why does the amplitude? This is it. Let me explain that. The moment we immerse the test tube first, you see the test tube goes down and up, down and up. At that time, the amplitude is much, which means you can really see, you can really observe it clearly that yes, this test tube is bobbing up and down. But over time, what happens is that the going up and down, the bobbing up and down begins to reduce. It's not like pronounced as you have at the start. So which means it's decreasing and decreasing and decreasing, and then it steadies over time. So why is it that the amplitude of the test tube decreases with time? It is very simple. It is because of one of the forces that you have here, and the answer to B2 is because of viscosity. Viscosity talks about internal friction. This is what we call liquid viscous force. That's what we call liquid friction, which opposes the motion of the test tube. So with that, we've been able to answer this question, and that is a whooping 25 marks. With that, we've come to the end of this question. If you need more clarity, all you need to do is visit 300plusacademy.com. When you do that, you're going to see various academic groups. Click on those groups on WhatsApp, of course. Join and meet with people preparing, with various scholars preparing for same exams, and you get the chance to directly DM us things you don't understand, things you need clarity on. And of course, for various exams you're preparing for, you can directly tell us what topic you would like us to, of course, treat here on our YouTube channel, and we'll gladly do that. Okay, with that, we've come to the end of this. Don't forget, like, comment, subscribe, and of course, turn on the notification bell, because everything we are going to be doing at 300 Plus Academy is slick preparations to make sure you are in place to ace your next exam.